Alright. Streaming, not streaming. Let's see. I am. Alright, back on hash table. And I said I would like convert them to use void pointers. But actually, I mean, I've done that 1,000 times for like 1,000 different data structures, and I don't think I would learn much from this. So I think what I would like to do instead is to just dive deeper into more optimized versions of a hash table. And so yeah, I think maybe I should start by adding a more reasonable hashing function. So I read that Rust is using a sip hash 1.3. No clue what the fuck that is. But if I can quickly get that in my implementation, that would be nice. Although there is no pseudocode, so maybe it won't be that one, but I'm still curious. Sip hash is an add rotate XOR based family of pseudo-random function created by those guys in response to spate of hash flooding. Denial of service attack. Hash flooding. In cryptography, a collision attack on a cryptographic hash tries to find two inputs producing the same hash value, i.e. a hash collision. This is in contrast to a pre-image attack where a specific target hash value is specified. So they're like trying to generate collisions on purpose, because like the most collisions you have in a hash table, the worse it gets. I guess that makes sense. Siphash is designed as a non-cryptographic hash function, although it can be used to ensure security. Siphash is fundamentally different from cryptographic hash functions like SHA, in that it's only suitable as a message authentication code. A keyed hash function like HMAC, that is... Okay, I don't understand the rest. Siphash computes 64-bit message. Okay, but I mean, if there is no pseudocode, hello, my favorite French dev. Hello, my Dimuxman. Yeah, I had no inspiration. I just ate. My mind is fuzzy, so sorry for the for the shitty name. Siphash. Yeah, maybe let's just have something decent from Stack Overflow first. Let's maybe like Google some of those and see what they're all about. By the way, if you're wondering, I'm like rewriting a hash table, and for now it's rather simple. Just have a very simple hash table where you can insert, delete, get, and check if a key is contained in it. And yeah, the implementation that I've done is called open addressing, meaning that it's just literally an array. You hash the key to get an index in that array, and if there is a conflict, you just go to the next one. So I'm doing linear probing, as they call it. So as you can see in this image, John Smith has a collision with Sandra D, and Sandra D just uses the next spot below John Smith. And if there was a key that had already this index, it will also, so Ted Baker should be at Sandra, like should be as a collision with Sandra D, But since she already exists, he takes the next spot. And then, so yeah, I've never implemented it like this, but I mean, it was very, very simple to implement. Less than 100 lines of code. So yeah. And now I'm just, yeah, trying to make it a bit better. By, I think I'm gonna try to like have a better hash function, because for now it's just like, my hash function is literally like iterating over the characters of my key, and like multiplying them together and like doing a modulo the size of the array, which, well, it sucks. It was just to prove to myself that it works, that the rest works. But so now, and then after that, I would like to try maybe quadratic probing, which seems interesting. I don't know, yeah, I'm just curious because that's what Rust uses. And also Rust says it uses a SIMD lookup. So yeah, I'm curious about that as well. DBM, small DBM, SDBM, file-based key value store. Okay, so there is... I don't know if those are like actually known stuff or hash, start in code. And that's the kind of web page I would like to see more often. So yeah, it seems simple enough. Written also known as DJB. This simple hash function dates back to 1991. Hash functions have wide application in computer science. For example, the hash function from this code snippet maps hello to this number, but hello to this number, despite the fact that there is only one character difference. Snippet explanation. Then it iterates over the given array of characters and performs the following operation on each character. Multiply the hash by variable by 33, add the ASCII value of the current character to it. So, so wait. Left shift by 5 is times 33. Is that right? Doesn't sound right. I mean, I know it's wrong, but like, okay, I mean, sounds like times 32 to me, but I don't know. Yeah, sounds like it's times 32, not 33. Oh, it does a plus hash at the end, so it is times 33. Okay. Add the ASCII value of the current character to it, so that's just plus C. And that's like the seed, I guess. Multiplying a hash by 33 could be performed by doing this, however the function uses this. Bit shift, we see main CPU faster, yeah sure. Couldn't like the compiler already do this optimization though? Yeah, feels like something that the compiler could figure out on its own. Multiplying a hash, bit shifts. Faster way to perform this operation. More information. The starting number 5381 was picked by DJB simply because testing showed that it results in fewer collision and better avalanching. What is better avalanche? Avalanche effect. In cryptography, the avalanche effect is the desirable property of cryptographic algorithm, typically block ciphers. Oh, okay, I see. So you just change like one little thing and it produces a completely different thing. Okay, it's called the avalanche effect. That's nice. Good to know. Ah, and it's just written by a guy whose initial are DJB. Okay. Okay. Huh. And and he's the guy who makes zip hash as well, apparently. Everything is connected. Okay. So there is this one seems very simple to implement, or Alder32. This one seems a bit less simple. Yeah, whatever. Let's just use the DJB one. So digest is equal to the seed. I mean seed. The initial one is this value. Then we do digest is equal to I guess digest left shift by 5 plus digest plus key, like so. And I guess at the very end we return this. That sounds about right. Yeah, the tests are still working. Let me just quickly add a comment that just plus 1 is equal to times 33. Yeah, that's... Yeah, sure, that's kind of understandable, at least for future Charles, I think. Alright, so we have a slightly better hash function. That's something, I guess. And it's a very simple one at that, so that's nice. Then I would like to understand what quadratic probing is. So linear probing is in which the interval between probes is fixed, usually 1. That's what I'm doing right now. Then we have quadratic probing. Let's see. Quadratic probing is an open addressing scheme in computer programming for resolving hash collision in hash tables. Quadratic probing operates by taking the original hash index and adding successive values of an arbitrary quadratic polynomial until an open slot is found. Adding successive value of an arbitrary quadratic polynomial. An example sequence using quadratic probing is h plus... Okay, so instead of checking the next one, we check like kind of the index exponent 2 every time. So we try like powers of 2 every time instead of trying the next one. What is the advantage of that? Quadratic probing is often recommended as an alternative to linear probing because it incurs less clustering. In computer, I guess that's where there is a lot of collision at one spot. And since we're doing we're doing exponent 2 every time, like it's going a bit, it increases, I guess, the randomness of where the collisions are stored. It incurs less clustering. Okay, quadratic probing exhibits better locality of reference. Is that the fact that we can fit more stuff in the cache? Locality of reference, also known as principle of locality, is the tendency of a processor to access the same set of memory locations repetitively over a short period of time. So yeah, I'm guessing this is cache locality, kinda. But I wonder how it could have like better cache locality since we're just going all over the array. But like if you do linear probing, you just go one by one, which in my opinion should be better, I feel like. Less clustering, quadratic probing exhibits better locality of reference than many other hash tables, such as chaining. However, for queries, quadratic probing does not have as good locality as linear probing, causing the latter to be faster in some settings. Okay, so yeah, it's just what I thought. Like, it has better than many other hash tables. So it's better at locality of reference than chaining, which I don't know what it is yet. But it's worse than linear probing. Quadratic probing was first introduced by this guy. Recommended. So wait, it is recommended as an alternative to linear probing because it incurs okay, less clustering, but worse locality of reference. Okay, yeah, that makes sense. That makes sense. So you have just no, like you reduce the chances of having like big blobs of conflicting keys in your array. Instead, like you spread the conflict a bit more evenly, I'm guessing. So yeah, that makes sense. And you're doing that as a price of slightly at the price of performance because you're doing exponent 2. But they do say like an arbitrary polynomial, quadratic polynomial. Not sure which one I should use. Should I just do exponent 2? Quadratic function. Okay. Where C2 degrades to a linear probe. Yeah, that I understand. Okay, and so we can like basically customize C1 and C2 to be whatever we want. Do they recommend something or round up to? Rounding up M can be computed by limitation, alternating signs, references. Example, if hk I is equal to hk plus I exponent 2 modulo m, then the probe sequence will be hk plus 2, hk plus 6, and so on. For m is equal to 2 exponent n, a good choice of constants are C1 is equal to C2 is equal to 1/2. This leads to a probe sequence of hk plus 1, hk plus 3, hk plus 6. The triangular numbers where the value increases by 1, 2, 3, and so on. Okay. For prime, most choices of C1, C2 will make H distinct for I. Such choices include 1/2, 1, and 0, 1. However, there are only m divided by 2 distinct probes for a given element, requiring other techniques to guarantee that insertion will succeed when the load factor exceeds 1/2. Okay, that sounds quite tricky, but I think the bottom line is I can just do exponent 2. Like there might be better things, but yeah. Wait, let me keep the reference to this above my hashing function. EJB hash function. Let me just keep the link somewhere close. Then the only time where I try to get a bucket, so that's where there is the conflict handling and so on. And so I think what we want is just that here we do probe times probe. Probe explain2 since quadratic probing reduces clustering. Sure, that sounds fine. And so I'm guessing maybe the SIMD part of this algorithm that I read in the Rust documentation is that here we have a for loop and we can like look up 4 buckets at a time, or like do this computation 4 at a time instead of or like how many AVX whatever we have. So we can do this computation 4 by 4. Which, yeah, I guess is fine. Okay. And so this should still work. Yeah, it does. But I'm still curious, what is chaining? I think that's the third one. Double hashing? Oh no, double hashing is something else. Oh, no. Okay, chaining is like a completely different thing where you have like a linked list or a dynamic array as your entries, so that you handle the conflict by just pushing them to the list of that bucket. Okay. And what was the disadvantage of this? Ah, yes, it has, chaining as poor cache locality, of course. In which the interval increase by... Okay. Double hashing, in which the interval between probes is computed by a secondary hash function. Ooh, that sounds even fancier. Double hashing in computer programming technique is used in conjunction with open addressing in hash table to resolve hash collisions by using a secondary hash of the key as an offset when the collision occurs. Double hashing with open addressing is a classical data structure on a table T. The double hashing technique uses one hash value as an index into the table and then repeatedly steps forward an interval until the desired value is located. An empty location is reached. The entire table has been searched, but this interval is set by a second independent hash function. Unlike the alternative collision resolution methods of linear probing and quadratic probing, the interval depends on the data so that values mapping to the same location have different bucket sequence. Ah, this minimizes repeated collisions and the effect of clustering. But yeah, my guess is that we use quadratic probing instead of this thing, just because I would assume it's faster to compute the next probe. Selection in practice, analysis, variance, triple hashing, enhanced double hashing. Kaku hashing is a scheme in computer programming for resolving hash collisions of value of a function in table. Huh. That looks crazy. Hopscotch hashing. There is so many. There is so many. Perfect hashing, what the fuck? In computer science, a perfect hash function? I thought that didn't exist. H for a set S is a hash function that maps distinct. Ah, okay. If you know, like, beforehand what the keys are gonna be, you can probably make a hash function that is perfect for this specific set of keys. And since in practice we often don't know in advance what the keys are gonna be, I don't think we can do that. That's nice. Huh. Alright. Anyway, fuck, I thought it was quadratic probing would take me a long time. But yeah, I guess I could make it more complex, but I don't see the point too much now. But I would be curious to hash table SIMD. I wonder how the SIMD optimization works. Well, I guess there is some dude that figured it out. Let's see. SIMD hash map. Get next cap. Wait, how long is this? Fuck me. Long. God damn, modern C++ is really giving me the chills, you know? SIMD metadata. What the fuck? Metadata. But I don't see any SIMD thing. Where's the SIMD thingy? Where is my MM265 at? Or 26 something, I don't remember. I don't know, do they have a readme? Intel processor include this. Compiler flags. Template parameters. Major differences between SIMD hash map and SIMD unordered map and STD unordered map. Okay, let's see if there is anything else. Rethinking SIMD vectorization for in-memory databases. That looks too long. Algorithms for linear probing. Hash tables have to have uses in the execution of joins and aggregation, as they are allow constant time key lookup. SIMD has been utilized to build bucketized hash tables where a probing key can be compared to multiple hash keys by horizontal vectorization. Where a probing key can be compared to multiple hash keys Isn't that just what I was saying, that I can do like this loop, like the probing loop? I can vectorize it, but yeah. Guess I can make those inline as well, although they would probably be inline by anyway by GCC. Not sure how they express that in that pseudocode. Linear probing, double hashing, cuckoo hashing, Bloom filters. What the fuck is going on? Partitioning. Okay. Characterizing SIMD-aware hash table designs on emerging whatever. Scalable KDF and password hashing theme. That looks like more different. SIMD hash table bench, characterizing SIMD-aware hash table designs on emerging. Yeah, that's basically what I just read, I think, but behind the paywall. Optimizing open addressing. Let me go fetch my hoodie. There it's optimizing open addressing. Your default hash table should be open addressed using Robinhood linear probing with backward shift deletion when prioritizing. Yeah, that's true. What happens if... Oh, I haven't tried this. Like this backward shift deletion, because like if you have like 3 collisions and then you have like you delete one of the value that collided, the previous ones, the next ones, need to be shifted back. No? I think so. Otherwise, when it looks up for it, it's gonna see that the key is null and it's gonna assume that it doesn't exist. Like the value that collided, not the value that we deleted. So... it's kind of funky. So on delete, to do, fix, wait, no, it's fix me, have to shift back the collided values. Yeah, I think it's not the worst thing to... Yeah, I'm thinking in terms of the video I will make later. I think I don't have to implement it 100%, just have to really mention it, that it's something important. I think without this, it still explains the goal of a hash table pretty well, or how it works at least. Using Robinhood linear probing with backward shift deletion. Robinhood linear probing. Not sure what that is. Robinhood. I've heard of Robinhood scheduling before, but linear probing, I don't know. When prioritizing deterministic performance over memory efficiency, two-way chaining is also a good choice. Two-way chaining. Is this the thing with linked lists? Yes, it is. Do I need the dark theme for this? Yeah, maybe not. Code for this article may be found on GitHub. Open addressing versus separate chaining, benchmark setup, discussion, separate chaining, linear probing, quadratic probing, double hashing, Robinhood linear probing, two-way chaining, unrolling, prefetching, and SIMD. Okay, sounds like it looks like a good. I don't know. Well, my bookmarks are a mess. Most people first encounter a hash table implemented using separate chaining, a model simple to understand and analyze mathematically. In separate chaining, a hash function is used to map. Yeah, I already know this. So you have an array of linked lists. Open addressing. Each bucket only contains a single key. Collisions are handled by placing additional keys elsewhere in the table. Okay. Unlike separate chains, open address tables may be represented in memory as a single flat array. A priori, we should expect operations on flat arrays to offer higher performance than those on linked structures due to more coherent memory accesses. However, if the user wants to insert more than k keys into an open address table with k buckets, the entire table must be resized. Typically, a larger array is allocated and the current keys are moved to the new table. The size is grown by a constant factor, for example, times 2. So insertion occur in an amortized constant time. So yeah, basically the array becomes a dynamic array, and when we run out of space, we reallocate by growing the capacity by 2, just like a dynamic array. Why not separate chaining? In practice, two of the standard libraries in many languages provide separately chained hash tables, such as C++'s unordered map. At least in C++, this choice is now considered to have been a mistake. It violates C++ principle of not paying for features you didn't ask for. Separate chaining still has some purported prétendu. Never heard of didn't knew that was a word. Purported benefits, but they seem unconvincing. Separate chain tables don't require any linear time operations. First, this isn't true to maintain a constant load. Okay, so basically they suck. Low memory overhead. Okay, so he's setting up a benchmark. That is fine. Hash function uses the squirrel tree hash function, fast integer hash that, as far as I can tell, only exists in this GDC talk on noise-based RNG. Other benchmarks. Separate chaining. Unordered map, linear probing. Lookup. Insert, starting from the keys index, place the keys in the first empty or tombstone bucket. Lookup, starting from the keys index, probe buckets in order until finding the key reaching a non-empty, non-tombstone bucket, or exhausting the table. Erase, look up the keys and replace it with a tombstone. So they have this concept of a tombstone. And do they mention it earlier? In the following diagram, assume that each letter hashes to its alphabetical index. The skull denotes a tombstone. Insert, starting from the keys index, place the key in the first empty or tombstone bucket. Okay, so they have some kind of special marking. They have like a distinction between an empty one and a tombstone one. So an erase, look up the key and replace it with a tombstone. And when they insert, when they look up, starting from the keys index, probe buckets in order until finding the key, reaching a non-empty tombstone, an empty non-tombstone bucket, or exhausting the table. Okay, so they have some kind of marking to distinguish between an empty or a tombstone. Okay, in my case, I guess I can just make like if it's empty or a tombstone, I make the key is equal to null, and if it's empty, I make the value equal to 0, and if it's a tombstone, I make the value equal like -1 or something. I mean, it avoids creating an extra boolean flag for it, I guess. And so the goal of this is that we actually don't have to shift back all the collided thing, I'm guessing. Erase, look up the key and replace it with a tombstone. Starting from the replay, place the keys in the first non-empty or tombstone bucket. So for insert, it doesn't care if it's either empty or a tombstone. For lookup, that's when it cares. So it wants it skips the tombstone and stops at a at an empty. Okay, I see. Yeah, for now, let's try to implement this using just dumb logic. Define tombstone is equal to -1. And what we do is when we do a delete, we don't do value is equal to 0, we do value is equal to tombstone. And so insert does not care if it's tombstone or empty, so this is good. Delete doesn't care either. Replace it with tombstone. The problem is gonna be there because I don't fucking know. I know I do know. because this only returns when it's a tombstone or an empty one. But for lookup, so for hash table get, we want to we don't want to care about the tombstone. We want to ignore the tombstone. How do I convey that in a clean way? I don't know. I guess for now I could have like a simple Boolean flag called skip tombstone, and I do if skip tombstone, and you can do that here. So if the key is null, it's that it's either empty or a tombstone, and if we do if not skip tombstone, if we don't want to skip them, and the bucket value is equal to tombstone. So if it says tombstone and we don't want to no, and we do want to skip it, we do continue. Does that sound good? I think it does. So for those, we don't want to skip them. For delete, we don't want to skip them. Wait, we do want to skip them. I'm getting so confused. Look up the key. No, okay. Delete is a lookup, so we do want to skip them. We do want to skip the previous tombstone, but like replace the one we find by a tombstone. Okay. Oh, for fuck's sake. And then get, we also want to skip it there. So it's only on insert that we allow it to be a tombstone. Okay, yeah. Okay. Does that still work? Yes, it does, but I'm not testing this, of course. Okay, so at least now that's like a much cleaner way of handling deletion, because I don't have to like shift entries around like a stupid person. I can just like mark them like as a tombstone, like it's like saying they don't exist anymore, but they so it's like they don't exist anymore, but what? But like they're marked as being part of like a potential chain of collision, or like a group of collision, so that we know how to handle it when inserting or doing a lookup. Okay. The results are surprisingly good considering the simplicity. Did they explain that in Wikipedia, and did I just not pay attention because I'm a dumbass? Caching and locality of reference. This graph compares the average number of CPU cache misses required to look up elements of a large hash tables far exceeding size of the cache with chaining and linear probing. The linear probing performs better due to better locality of reference. So, though as the table gets full, its performance degrades drastically. Ah, yeah. So in linear probing, of course, if you run out of space, if you run out of spot where to put somewhere, it has to like go, has to loop over a lot of probes, and so that's why it takes more and more time. Okay, but when there is like a normal amount of elements in it, it is faster than chaining. Okay, that makes sense. Robin Hood checking collision resolution algorithm. Hmm. Yeah, I would also like to implement dynamic resizing, which would be fun, I think. Alternative to all at once rehashing. And so yeah, since you need to like compute the new places of the thing, that could be tricky. Caches, transposition table. Erase rehashing. One simple optimization is automatically recreating the table once it accumulates too many tombstones. Erase now occurs in an amortized constant time, but we already tolerate that for insertion, so it shouldn't be a big deal. Let's implement a table that recreates itself after erase has been called n divided by 2 times. Clearing the tombstones dramatically improves missing key queries, but they are pretty slow. They are still pretty slow. Okay, so I guess yeah, if you have too many tombstones and you want to look up something, like it's gonna ignore a lot of spaces before arriving at the correct entry. So yeah, I understand. It's like when once you reach like some number of tombstone, you just want to have like a clean slate. Okay. Erase backward shift. Actually, who says we need tombstones? There is a little thought, but very simple algorithm for erasing keys that doesn't degrade performance or have to recreate the table. When we erase a key, we don't know whether the lookup algorithm is relying on our bucket being filled to find keys later in the table. Tombstones are one way to avoid this problem. Instead, however, we can guarantee that traversal is never disrupted by simply removing and reinserting all following keys up to the next empty bucket. So, okay, so we want to remove B, and what is gonna happen is that we're gonna just recompute C and H. Note that despite the name, we are not simply shifting the following key backwards, as any keys that are already at their optimal index will not be moved. Okay, after implementing backward shift deletion, we can compare it to linear probing with rehashing. Naturally, erasure becomes significantly slower, but queries on missing keys now have reasonable behavior, especially at the 50% load. In fact, at 50% load, this table already beats the performance of equal memory separate chaining in all 4 metrics. Okay, so not having tombstones is better. Except for erase, of course. Quadratic probing. Quadratic probing is a common upgrade to linear probing intended to decrease the average and maximum probe length. Can be efficiently computed by adding n to the index at each step. Okay, so this is like the triangular numbers, if I'm not mistaken. So yeah. There actually is a true deletion algorithm for quadratic probing, but it's a bit more involved than the linear case and hence not reproduced here. We will again use tombstones and rehashing. Okay. After implementing our quadratic table, we can compare it to linear probing with rehashing. Okay. Yeah, this looks a lot better. Double hashing purports to provide even better behavior than quadratic probing. Instead of using the same probe sequence for every key, double hashing determines the probe stride by hashing the key a second time. That is, a probe of length n queries the bucket at index h1k plus n times h2k. Okay, what the fuck is going on? I don't know anymore. But basically you have a second hashing function to discover like the index if there is a collision. Double hashing succeeds in further reducing average probe length, but max length are more of a mixed bag. Unfortunately, most queries now traverse larger spans of memory, causing performance to lag quadratic hashing. Yeah, I guess, yeah. Since the next probe are a bit random all over memory, it's harder for the CPU to keep everything in the cache. Although for quadratic probing, it's like worse than linear probing, since it's also a bit random, but it's still like the first few elements are still contained in the same area. Where this is like completely random, I would say. Robin Hood linear probing. Fuck me. Two-way chaining. Unrolling prefetching and SIMD. Software prefetching, SIMD. Yeah, okay, I think that's what I was imagining when I thought of SIMD for this. That was I mean, this is a good blog post. I haven't read it all, but I should save this guy's page. Oxidizing C++. I'm guessing Rust. Yes. Damn. Oxidizing camel. The fuck. Humming hats. Jersey City, Pittsburgh. Okay, I'm getting very distracted. We went from hash tables to cool vacations. My CMU course. What the fuck is CMU? Okay, sure. I'm still a bit curious about this, but the noise outside is making me go cuckoo. So, all right, Robin Hood linear probing. So far, quadratic probing and double hashing have provided lower probe length, but their raw performance isn't much better than linear probing, especially on missing keys. Enter Robinhood, linear probing. This strategy drastically reins in maximum probe length while maintaining high query performance. The key difference is that when inserting a key, we are allowed to steal the position of an existing key if it is closer to its ideal index, richer than the new key is. When this occurs, we simply swap the old and new keys and carry on inserting the old key in the same manner. This results in a more equitable distribution of probe length. Okay. This insertion method turns out to be so effective that we can entirely ignore rehashing as long as we keep track of the maximum probe length. Lookups will simply probe until either finding a key or exhausting the maximum probe length. Implementing this table compared to linear probing with backshift deletion. Okay, I'm not implementing this. This seems, or at least not today. Let's see. So there is two to-dos, like recreate the hash table when there is too many tombstones, half table is when half table is tombstones. Since tombstones causes lookups to be slower. Okay, and yeah. Second to do is make the hash table in a dynamic use a dynamic array instead of fixed length. Yeah. To avoid crash when running out of buckets. Okay. What have I modified since last time? I've changed the hash function. I did quadratic probing and added tombstones. Okay. Let's I don't know, change hash function to dg b fix deletion by adding tombstones. What else? What else? What else? Yeah, I don't know. By adding tombstones, and what else did I do? What else did I do? Ah yes, quadratic probing. Add quadratic probing. Nope. No GPG sign. Rates. Let's maybe yeah, make it into an array already. Like a variable length array. Yeah, not really a variable length array, but like you understood what I was saying, like a pointer to an array so that I can malloc it. And so in the new, we always have like a size t now. And here we will have a size t capacity. Yes, need to include std lib. So I'm guessing we need this here as well. Size t capacity. And we do ht capacity is equal to capacity. Yeah. And then we need to do ht buckets is equal to actually we don't need to pass the capacity here, I guess. We can do the same thing as dynamic arrays, where it starts with a capacity of 0 and then buckets is equal to just null. Hash table destroy, I'm guessing, is going to be here ht capacity and buckets count again. Guess we can have a hash table here, ht. This is just ht, and this is just ht capacity, ht capacity, and this as well, I'm guessing. Okay, yeah, that seems fine. Then I need to count the occupied buckets. Buckets. Is there like a special name for it, or do I just not care? Yeah, it calls them empty or non-empty or by the count, I guess. I mean, maybe I could call it length, but that feels wrong. That feels wrong. So when we start, occupied count is equal to 0 as well. And then it's only when we insert we need to do we need to do if ht occupied count is greater is greater or equal than ht capacity. We need to do something, but it's more complex than a dynamic array. What does the Wikipedia page say about this? So, dynamic resizing. Repeated insertion causes the number of entries in a hash table to grow, which consequently increases the load factor. To maintain the amortized big O of 1 performance of the lookup and insertion operations, a hash table is dynamically resized and all the items of the tables are rehashed into the buckets of the new hash table. Since the items cannot be copied over as varying table size result in different hash value due to modulo operation, if a hash table becomes too empty after deleting some elements, resizing may be performed to avoid excessive memory usage. Okay, maybe I'm too fucking tired and to do this. So I need to locate larger buckets array rehash all keys in the new array. Could I mean, I could do it in a slightly weird way, but I guess I could have like a with capacity and like size t capacity, and here capacity is capacity, and just make that like new void is returns hash table with capacity of 0. Is that C or C++? It's just plain C. There is 0 C++ involved. And so here we generate a capacity, and then what we want is again xmalloc. Yeah, I guess I'm not really using realloc in this case, but yeah, I don't think I can. Xmalloc of capacity times size of struct hash table entry. There is no hash table entry. I know I called it a bucket, right? So this, yep, sounds about right. I guess this can be static for now, I don't care. And so here we can do hash table, I don't know, new. I would have loved to participate, but I absolutely suck at C. I only did it in college and c'est tout. Yeah, it's fine. It is fine. Not the most used programming language, or at least in like the regular industry, at least. Hash table new is equal to hash table with capacity, which will be ht capacity times 2, I'm guessing. I guess we can do growth factor here as well. And you just do static const size t growth factor is equal to 2. Yes. And then what we need to do is for size t I is equal to 0, while I is lower than ht capacity I plus plus. So we're gonna iterate over every single bucket in the thing. We do if ht buckets I key is equal to null. So if it's like either empty or a tombstone, we don't care about it, so we continue. If it is not, we do hash table insert into ht new, and we insert ht buckets key, ht buckets, wait, no, buckets I value, like so. And yeah, that's pretty much it. And at the very end, so this will take care of the rehashing of everything like we want. And then at the very end, we do free. We need the destroy thingy up. We free every single one of those. This is extremely inefficient. Cert, no. No, I understand myself. Because here I'm like redoing a copy of every single string every time and like freeing them after where I don't have to. And so after freeing every single thing, and we can free the ht buckets themselves, which we also need to do here. Which we also need to do here. We need to do if ht capacity is equal to 0. We need to set the capacity equal to, let's say, 2. Or maybe 1 is fine. Because otherwise it's going to be 0 times 2, and it's always going to create a hash table that is of length 0. Then once we have like reinserted everything, we need to do the ugly bit where we do buckets is equal to the ht new buckets. The capacity is equal to ht new capacity. And the occupied, actually the occupied count should not change. And actually here ht occupied count plus plus, and when we delete one, occupied count minus minus. What are buckets? So yeah, buckets are just one element of the hash table. So I'm not sure if you know how a hash table works, but like you can see that it's just a big array, and then there is a hash function that does a mapping between, like, I don't know, for example, a string, could be anything, but let's say a string, so in this case a name, and hashes it down to like a number, which we are going to use to index into the table, and just each element of this table is called a bucket, where you have the actual value associated with that key. So yeah, buckets are just elements of the array. And so yeah, I have a struct here called hash table bucket, which is just a struct that is a key and a value. And yeah, so hash table is just basically an array of those buckets. Okay. So this is getting messier and messier. And once we have done this, so the buckets is there, but then we need to free actually the ht new. Yep, that sounds about right. Which is kind of an ugly way of doing it as well, but you know, it be what it be. Alright, and then we have this, and yeah, it's just a regular insert after that, I guess. Yep. Yep. Alright, does that even work anymore? Okay, it does not. Buckets count. But there is no buckets count anymore. Oh yeah, it's in test HC. It's in HT capacity. Yeah, of course that will kind of. Oh, okay. So 40. So the delete one does not work, the insert. So yeah, I'm guessing I broke the insert. Probably broke the insert. Oh well. I think I'm too... I see. Hash tables... oops. Hash tables are said to be big O of 1 time complexity when accessing a value or adding into it. Doesn't the hash function make it take longer than big O of 1? Well, I mean, still constant time since you're doing the same operation, you know? Like the hashing function is does not depend on the number of elements that you have in the hash table. Like it depends on the size of your key and the complexity of the hash function. But so in my example, I have a hash function that is just a little loop over every character in the key. But when we're talking like big O notation, I think it's more like regarding the, I mean, general, when they say this, it's regarding the number of elements in the hash table, not like the length of the key or like the complexity of the hashing function. So yeah, I think it's still most of the time big O of 1. Yeah, but then if you have collisions, it becomes something else. That's why you need to minimize collisions. Alright, yeah, I think I will stop here. Because I'm getting just tired. I did learn a shit ton of stuff about hash tables and the different ways of implementing them, and yeah, how you can optimize them and so on and so on, which was really cool. So yeah, we'll stop here and see you maybe in the next one where I finish this hash table thing, or not. Maybe I just got lazy. What other programming languages are you proficient in? Mainly Python, but I don't like writing in Python. I don't know, C++, Rust. Proficient, I don't know, Golang probably. I'm proficient. But otherwise, yeah, I've written quite a decent amount of Haskell, Lisps. Yeah, I don't know, just a bit of random programming language all over the place. So yeah, that's it. Hopefully that I answered your question. Yep, see you. Go or Rust, both. Why not both? Alright. Anyway, the music outside is making me go freaking bonkers. So I'm gonna stop.